Okay, so first of all, I would like to thank you for the invitation for this. Really, I think it's really wonderful conference, and there is a lot of interesting ideas coming on. So my talk will be about distortion, imagining geodesic subspaces on shape ensemble, and it's more about okay, we could say manifold learning, and maybe some worry I have about. We see that we have more and more models now coming out, and so I think that's will lead to maybe with when we have data, and will be to know how to select. And just, okay, so this is more or less the story I want to tell you. Okay, so maybe I will use this. Okay, yeah. If I don't plug this.
That was risky.
Yes, that was risky. It works. It works. Okay, so I would like to. Okay, yes, to start from Darcy Thompson, and thank you, Peter, for pointing us this wonderful paper that appeared in the Wired magazine by Stephen Wolfram, and I picked this picture from this paper, and okay, clearly. I think that the interesting point about Darcy Thompson, okay, there is a lot of interesting points, but I think it's that I think his work is being considered as quite important from different disciplines, mathematicians, physicists, and biologists, and so on. And I think we all, and I think it's because he's trying to put different pieces and try to make sense of different point of view, and I think we have to deal with this is the kind of thing we need to do, is to try to put all the pieces, and there is a lot of questions in his works, I think, which are still unsolved. And so what we've done a lot with this theory of transformation, everyone knows, by Darcy Thompson. I think that okay, computational anatomy is more or less some kind of modern say incarnation of this theory of transformation. But I think, in a sense, in a Darcy Thompson work, it's not, there is not just the theory of transformation. He's asking many things coming from physics about how things grow and so on. So it's not a pure geometrical theory. It's asking more questions. And I think we can make some connection with, I think, this quotation from Ulf Grunander, which is, thinking in terms of pattern theory, is that in fact we have shape, we have deformation, but we not just want to do registration, but we want to have some kind of an interpretation of what's going on. So the question, it was a question by Grunander, which is, can we mechanize human intuitive understanding of biological pictures that typically exhibit a lot of variability, but also possesses characteristic structure in his book Hands. And I think it was in Florida, we talk a lot about Ulf Grunander. And I think this is still some very important question. And I think we are not yet able really to answer to that question. I will not answer also, but I think we should not forget this thing. So if we start, I think, so if we start with the general framework we are using, and it's the most, I think the most effective one at the moment is to work with the right invariant structure. So I will call it briefly. So where is the pointer? Here. Okay, so, and it's come back from Grunander. So we have a group action. We say that we have a shape space which will be a homogeneous space, so generating by template. And the thing is that if we start from a right invariant distance on the group of transformation, the group of mainly diffeomorphisms, which is right invariance, then we can get a metric on the homogeneous space of shapes by just trying to minimize the distance between the identity of ng for all g transforming m in m prime. So we get this distance. And we have, okay, in some good situation, we have a Riemaniann framework for that. Okay, we have this kind of thing. And so the idea is we can tell it in many different ways, is that we have a correspondence between, for a homogeneous space, between the point in the homogeneous space and fibers in the group G, and in fact we are computing distance between fibers and the right invariance distance. I think we know that we don't need to have right invariance. If we have right invariance, in fact that's a generic way to be sure that we've got distance on the manifold M. But okay, basically we will compute distances between these fibers. And so, why this is simple, why this is effective? Because we need to just define the metric in the tangent space of the identity on the group, because on the group to have a right invariant distance we just need to have one metric. So I think it's very simple, and you can build a lot of distances in different group of different shape space, and we have some consistency between the different shape space. So that's why I think it's quite effective. However, I think this okay, what kind of freedom we have? I think if we stay in the right invariant setting, we can play with the metric, and so there is a lot of things we can do with the metric. And changing the metric can be very important. It can be a large impact on the kind of distance you build. So this is the kind of thing we can do. This is still non-parametric, or we could try to have a more parametric modeling. And we could say that, in fact, we would like to have to put some prior knowledge, or to have something which is more, I should say, shape-aware metric. Because if we think about shapes are something which is not just passive. And in the right invariant setting, basically what we are doing is that we are transporting shape passively by deformation of the ambient space. So in fact, this is an assumption which is not completely resolvable from a biological perspective. Okay, so we could like to have more information on this. And so there is different attempt in the direction. I will maybe this we can start with this polyrigid and polyaffine transformation. It has been proposed by Arseny, where we have local piece of transformation. There's work by Greenender and Srivastava, and the idea of Laurent Younes about constraint diffeomorphism shape evolution. And this is what, more or less, I will recall it briefly, what explained Barbara Gris yesterday, is that, in fact, we can think that we have a shape, and given a shape, I think this is some kind of rephrasing of this, of a general framework, but we could say that for a shape, there is some kind of control you have, and given that control, okay, this is the shape, this is the control, and you can define a vector field. So you define it, an infinitesimal deformation of the ambient space. Now you have we have a feedback action. When you have a deformation of the ambient space, you have to transport your shape or your geometrical descriptors, and you have a cost, and you get this kind of picture where you have this. Okay, Barbara showed it yesterday, but we have this. M is okay. She called it geometrical descriptor. It can be okay. It can be some very small local things, but it can be also something which are larger. And you have this field generator, which given some control, the way the shape tries to change. And now you have some feedback action, which is given by the infinitesimal action and a cost. So we have this beautiful picture. And the thing is that, given this, in fact, we can build a sub-Riemaniann framework. It's mainly a sub-Riemaniann framework. When we compose the field generator with the infinitesimal action, you get a distribution, what we call a distribution. We define the sub-Riemaniann structure, and when we have this uniform embedding condition, which means that in fact we can embed continuously the fields generated by the cost, by the control, and weighted by the cost. You can control the cost you choose at a given position M. You can control the square of the norm of the vector field. So when you have this, you can have a sub-Riemaniann distance, and you can define this. Okay, you can do what you want. So it means that it's not so hard to define some general setting. And we can control the smoothness. So there is a way to say, okay, I do not precise what I mean by the Hamiltonian is CK, because we have to be precise. But the fact is that you can define the Hamiltonian, and you can do shooting if you want. So the thing is that in this, okay, there is two things. First is that we have this compositional framework, is that we have this local, in fact, the thing we have to think about this as the deformation module, which are defined locally. And we have a way to compose it. So we get this, all these different modules, and they interact, and they give something which is global. And so the fact is that you have in this, okay, the composition is mainly, in this framework, is mainly additive composition. So it means that the module can define a vector field, and all the vector field adds, and this is a global, the sum of all these vector fields which will deform the shape itself. So it's really, it's not like the case Laurent presented this morning, where it's really sub-Riemannian. And in a sense, here, if you think about the momenta are usually given by the number of objects you have in your discretization, if this is discretized, or it's in the cotangent space of M, and it can be much larger than the actual control you have, but you cannot reduce it. You cannot say, there is no way to say that in fact the real degree of freedom is given by the number of control. It's much higher. So it means you can really do all these weird things that you can do in okay, so this is a simple example just to have a story. So I computed by Barbara, where we have these two skulls, and we have different models. I will not explain what they are, but you can think the triangle is about something which is scaling, you have rotation, you have some kind of translation, all kind of concentration. This is some very simple example, but the thing is that here there is this idea that in fact you want to define, you have all this control, you have where you can act on all these different models to produce an overall infinitesimal deformation. But you want to have something where you can interpret, I'm not sure this is really interpretable, but the thing is that you want to say something about what's going on. So the triangle here, the control, it means, okay, when you want to go to this curl, to this one, basically you see that you need to scale the scale, to grow the scale. You have different movement, and you have to have this kind of semantic interpretation, which is about what Grinder wants to do. Okay.
Fire?
What?
What is below the arrow, the curls? Does it?
The red ones?
Fireworks. Yeah, it's.
The red. The red. This is the control value. This is the control value, and yeah, this one.
Yeah.
This means that in fact, when you see this red, it means that in fact you want just to create a field which is just creating a growth here. So you can read it. So in a sense, okay, I'm not saying that's trivial to read this kind of math, but in fact it's a way to say something, to try to write a script about what's going on, not to have just this thing, but to say, okay, we can read at this different object. And I think this kind of idea, maybe this one or another one, I think it's still something important. The cool thing is that in fact we can build the Hamiltonian from that, we can shoot from that, even we have all this machinery, but this shows just that in fact it could be really interesting to really play with this kind of metric, but now we can build a lot of different metrics like that. And in fact, we don't really know how to select between these different kind of metric. We could say there is somewhere the metric, but I don't believe that when they have data sets. So there is a story and how to select, how to remove this, how we can do that. Okay, so here you see this is the evolution of the grid at the end. So what we are doing is that we are facing a myriad of different models. We have a lot of models. We are now, because we understand more or less, more and more the machinery, how to deal with that, how to build this kind of things. But I think it is still, I think we are building molds, but we don't really, how can we try to do from that to learn something really with that model on the database, on the shape ensemble, how we can compare the different models, and so this is a question I think we have to face right now. So one could be, okay, so the challenge is how we can select a low dimensional representation from this. So it will be more about manifold learning. I will tell it immediately. And can we do something about comparing two or many models in some kind of practical way? Okay, so the idea of searching the manifold, I think that there is a simple idea, which is which is just to use the exponential mapping. So it means that in fact this is a tangential representation. So we have the tangent space. We know how to shoot, and in many of these models, you know, even the last one with deformation modules, we can build a Hamiltonian. We know how to shoot. So we know how to really compute this exponential map. So given some initial momenta, we get an object in the shape space M. And the thing is that usually what we have is that, and it's not usually, I think it's every time, except in some very toy example. Every time I think the data are never living in that space. The data are living outside that space. So we need a noise model. We need to have a distortion. That's really, I think, there is very few real examples where you can say that you have a Riemaniann metric and everything can be done in just this Riemaniann stuff. I think it's very hard. So usually you have a cost which has a data distortion, and which can depend, which give you how you're happy with some built shape. Usually it's some kind of distance with the observation, some kind of noise model. And the thing is that when we want to, at least just to do some kind of shooting, to shoot towards some object, what we need to have, we need to minimize this quantity plus the square distance. But for this quantity, we have to compose more or less with the exponential mapping, and now we know how to do this. Now we have piano, we have PyTorch, and the only thing we know how to deal with this. And if you know how to compute the derivative of u just by using the chain rule, I think you can compute the gradient of this kind of mapping. Okay. So we can solve. Usually, what we are doing is that we are solving the sum of the square distance between the template and the constructed shape M1. And this square distance, we know it because we have the Hamiltonian. So the square distance is given by the value of the Hamiltonian that you compute for the initial momenta, plus this noise term, and we really need it. We cannot avoid to have this. So the kind of, if we want to do data reduction, what we are doing, so we have seen a lot of possibility in a previous talk, but I will just mention this TPCA, I think, which is practically what people are doing the most. As, okay, you have your database, and you will solve n template subject problems, from which you get a collection of initial momenta. So it means that's a way to present your shape inside your tangent space. And what you do is that, okay, for this you do the joint equation, and after you compute PCA, and you get a representation, a subspace in the tangent space or in the cotangent space. And from that, you say you can define some kind of generative model for the data. Okay, but in fact, the problem is that when you do this, to compute this, you need to have your metric. You need to compute. You need to have to use this to choose your regularization model or your metric. You need to compute the weight between the regularization and the data term. Usually, you need to have this. Okay, we know that we can do statistics there for that, and there is a lot of interesting and important things which are going on, and we can use Monte Carlo method, SIEM, and maybe other things, and there is a lot of work we can do like this, but it's still hard to really estimate this. For the PCA on momenta, there is always a story about what we'll use, what kind of metric you can use. So you can use the L2 metric. We know that's bad. We could use the intrinsic metric, that's better. But we know that PCA is done without any relation to the noise model. So, and now, and the question we need to address is how to compare different alternative models for representing the data. And so we could look at the log likelihood, but in fact that's really hard to do it practically for this in the kind of setting. So the kind of idea, I say this simple idea is to say, okay, can we try to remove the rigorization? You know, when we do this shooting, we have the square distance of the square distance plus the data attachment term, and to say, can we just remove the rigorization and just consider a dimensionality constraint? I will explain that. So it seems absurd because if you remove the rigorization and you just minimize this, for instance, this kind of thing, you know that you will be overfit. You will overfit in many different ways. So you cannot do this. That do not make sense. But you could say, you could put now the dimensionality constraint in the following way. We say now consider a subspace Z of the cotangent space, and you fix the dimension R. And now we know that if we consider the mapping from any element Z, and this mapping is going from Z, and it computes the what? It computes the distortion you have towards your data, given by the constricted shape, which is the exponential. So you shoot in direction Z from M0, and you compute that. Okay. So we can consider this mapping. Now, what we know is that we have this given a subspace here. Thanks to this mapping, we define, in fact, in the object space, we define a geodesic subspace, which is given by all the kind of shooting you can do just using Z in this big Z, which is a R-dimensional subspace. So you have this dimension is fixed. So you look at all the things you can generate. It's defined R-dimensional submanifold, and we know that if you change your subspace, you will define a different manifold in the shape space. So you have, in fact, these subspaces are parameterized by the selection of a R-dimensional subspace in the cotangent space. Okay. So in this situation, so now what about the U term? So I will talk about this the shapes, geometrical shapes, and so I think a distortion which looks to be quite effective in many applications and interesting could be something. Okay, we can have different one, but I say we have the varifold representation. We say that in fact when you have your shape, you can consider it as varifold. And this transformation is nonlinear, in fact. And now you can compute the square distance between your observation. This is a varifold associated with the observation. And so we can always think an observation as a varifold, a shape as a varifold, and we compute this. And so I think this is a distortion which is quite interesting. Okay. So what we could do is that for searching some manifold, we could say now what we can do is just for any collection, you have n subjects, n is the number of subjects, for any collection of momenta, Z1, Zm. With the conditions at the rank, you have a control, you have a complexity control, which is given by the dimension of the vector, which is spanned by all these momenta. Then we could say, now, given this, given the fact that I can choose n is much bigger than r, but I have to choose momenta such that, okay, the space generated by this momenta is just of dimension r, and I will just minimize the distortion. So there is no more rigorization here, no more weight between the two. It's just a distortion. It's a pure distortion term. But I put this dimensionality constraint here. So the thing is that metric has disappeared. No, the metric has not disappeared, because when you change the metric, you will change the exponential map, and you will change the kind of manifold you are building. So in fact, you say choosing the metric is a way to define a lot of interesting submanifold in some shape space. So you have still the metric is there, but you think just is there to create all this subspace. But now, when you want to select it, you say now when you have this, it gives you some rigidity about the kind of thing you can build in shape space. But now you just want to minimize the distortion. You forget this. So the metric is there, but after the control, instead of having this rigorization, you put just a dimensionality control here. Okay, usually this is finely dimensional. Okay, you can compute distance, and so we can, in fact, it's related. I think it's you have a trivial identification when you have a finely dimensional subspace, and this collection of, so you could have coordinates for all this z, and so now you get a matrix. You get a matrix which is with n columns and the number of rows which is given by the dimension. It could be an infinite dimensional matrix in some sense, but okay, usually it's finite dimensional. And what we say, we want to have this matrix should be of rank R. Okay. So I say a little bit about this data attachment term. We have seen it more or less in Iran talk, but very briefly. So usually when you have shape, we have a collection of landmarks, we have triangulation, we know how to, we have lines, triangle, and all more, okay, depend on the dimension. And so we have the action on the, okay, so the shape will be coded by this collection of landmarks, and the action will be just a transport of landmark. And we have the embedding varifolds, which is very important because we have to have something which is invariant to parametrization. We want to work, in fact, in the Cachan space usually, because it's not so easy to have landmarks, but I will go back to that problem. And so the varifold is, in fact, we could say that the varifold is a distribution of tangent spaces with localization in some way. And so we could say, for those who know varifold, I don't need to say more, and for the other one I could say that what you have is that you will discretize your mesh. You could say you have a mesh by a sum of some object where you have, for each triangle, you have the surface of the triangle plus some Dirac measure, which is the Dirac measure in, which is where you have a localization, which is the center of the triangle, and we have something which is a vector space, which is coded for the tangent space. So we have this code for the geometry. So we have this thing. And now, so it means it's okay, we see that the connection between a list of points and this is a nonlinear mapping here. And we compute this discrepancy. Okay, for the gradient scheme, what we can do is that the idea is that, okay, the way is that we have, we can consider that the rank R matrix is a Riemaniann submanifold of Rp cross n if we have a basis of the tangent space. And so we can do a gradient descent. A gradient descent on this, we could say it looks like the Grassmannian. In fact, it's not the Grassmannian because we need to have, it's not just tangent space, but we need to have a list of Z1, Zn. It's not what, yeah? And practically how to do it, in fact, okay, that's a restrict. In fact, it can be quite a huge thing, but the fact is that the real dimension is we need to have a frame of this tangent space, and after for each z we just need to have the coordinates. So we have a factorization, and so we can do the gradient in this factorization. But the trick is that to use, in fact, really do the gradient in this nice Riemaniann submanifold, but to pull back the metric in the factorization, and so to compute things just using the factorization, which can help you to save a lot of data, but in fact to do the real Riemaniann gradient. We can use stochastic stuff. Okay. Stochastic gradient. Okay. So what I want to say is that this shares some common framework with the matrix completion problem. It's really, I think it looks like some kind of nonlinear version of a matrix completion problem. Why? Because in fact, what you have is the matrix completion problem. You have a matrix which is, we have P, here we have P rows and N columns. And we observe the classical problem is that there is some missing entries. So we do not observe all the entries. And you want to recover. This is a Netflix problem. Okay, it's a very well-known problem now. And we would like to recover the full matrix just seeing not all the entries, but some of them. And so basically, the idea is to use this rank constraint to say that, in fact, for some reason, for some physical reason, or because the world is simple, the rank is, you can fix the rank. So you look for matrices of given rank, and you want just to minimize that. And so there is some missing term. And so what you get here, this is you have all the rows, and now for each rows you have your observation where you have missing entries, and you try which is zi star. This is observation, but you see you have this projection. You have a projection because you have missing entries, and now you try to find a zi which is close to this. But what you are doing, you put this constraint here, you have a sum, and you see there is no regularization in that term, and you have just a sum, but you put some rank constraint here, okay? And so, in our saying, I think this, the linear projection, which is given a column, which is just a projection, you have the column, and what you get, what you generate is just, you suppress some entries, omega I is the entries you're suppressing, is replaced by the composition of two fully nonlinear mapping, which is first you have the exponential mapping, which is given by the metric, and the other is just given M to transform it in a varifold. And so in a sense here, it's something which is, I think, interesting is that since we have reparametrization invariance, because we are using varifold, in fact there is a missing information. The parametrization has disappeared in a sense. So there is also a missing information. In that nonlinear mapping, we have a missing parametrization, which is missing information, which is where is the parametrization is gone away. So a challenging question is to know if we, without any regularization, we can recover, I think, a consistent reparametrization of our object. So I want to say a little bit more about that. There is just to see about a very simple framework, just to understand what I mean by this problem. So imagine that our model is just some linear model. So S is just, we are considering curves in RD. So S is just a parameter to the variable to define the parametrization. And so we can say that what we observe can be any, this is a linear model of shape. So we have, this could be the template shape, and we can add some perturbation by some hi gamma I, where gamma I is a parameterized curve. Okay, so we have this linear model. So now we have that. So the thing is that, imagine that if we could see the parameterization of all the shape, if you sample, you have different h correspond of, you could think about the different axes of deformation you can have. Seeing different gamma h, or maybe all of them, you could retrieve this decomposition by using standard PCA, okay? But now assume that we observe gamma h up to reparametrization. I mean, in fact, we cannot distinguish because we are using this data attachment term, and this is the situation usually we're facing. Usually what we are facing, we could put some kind of small landmark, small number of landmark, but we cannot think about having a full real parametrization. So usually we are not seeing this parametrization, so we have these two curves for us are indistinguishable, you know, because you cannot see that. This is all that story about the top space, and okay, I should jump, and the quotient space. So question, can we estimate curves gamma hat high, estimation of this, such that in fact we have, okay, there is no hope to say that gamma I will be equal to gamma hat I. But the thing is that we have a unique phi. It means that now if we deform shape up to a global parameterization, we can consistently follow the parameterization in the deformation process. This is the idea. So we have a consistent, it means here, I'm not saying that I want to be able to compute gamma I exactly. I have a phi, that's clear. But can I be able now, when I build my model and I look at deformation, in fact, I can follow my parameterization is consistent along deformation. That's not trivial. So in fact, it looks hopeless because you could say that if you have to have a solution to be a solution, what you need, in fact, you need to be able to reconstruct for any h. You need to be able that up to some deformation phi h, which depend on h. We can be any deformation depending on h. You want to be able, okay, you have a solution if you satisfy this kind of thing. It means that you could have a transformation rho of h, of I, gamma I hat, and you want to have this equality. This means that, okay, in my estimated model, given this parameters, rho h of I will build a curve which is this curve up to a parameterization, but this parameterization will depend on h. So I can have any different h. So I have a lot of freedom here. Okay? So what I say, phi h may depend on h, so we have an inconsistent parameterization across different h. It's inconsistent. So that's why now if you just do your job, you will get something which is inconsistent. However, we could say, okay, now if we fix the rank and if we assume the normalization, suppose that you have this and we assume this weak normalization constraint. I mean, okay, for some trivial reason, we need to have some hypothesis about rho. We have to say, okay, I have rho of 0, which is 0, and the Jacobian at 0 should be the identity. Otherwise, you could just make a linear change of variable and okay. So, and you say that even imagine that you have this mapping are smoothly depending on h. Can we prove that in fact, if we are following, if we are having that constraint, can we prove that in fact phi h is equal to phi 0? It means that we have, in fact, we are able to retrieve the parameterization consistently across different h. Okay, so I think that, okay, I have a conjecture. I think I have a proof, but okay, I'm not completely sure because I'm still working on it. So I don't want to write a theorem here. So I want to be cautious. I write a conjecture, which is assume that in fact you have two conditions. Okay, this one says that in your linear model, it's such that for any given possible shape, gamma h, the tangent gamma prime of h, this is the tangent at the localization h, and gamma prime of I of s is linearly independent. It means that in fact you cannot move tangentially. In fact, you can do in some place, but almost for every s you cannot have something, because otherwise trivially there is some counterexample. Now it's some kind of identifiability condition for the fully observed problem. It means that in fact you should say that this condition says that you have time S1 SB such that this matrix is a full rank R. If this is not true, it means that in fact the different curve are not defining a space of R dimension. So it means that in fact your model is not built. So in fact you can need very few. For instance, if you are in dimension 2, if you look at planar shape, in fact, okay, this, if you think about that, you can just need and if R is equal to 1, if you have just a one-dimensional model, in fact you just need to have 2 points, or 1 point is enough to have this. So conjecture is, now, if you think that you have a local consistency, if on these points, we can be very few, and for instance, for open curve, if you have an open curve in dimension 2, and if R is equal to 1, you have just by the boundary, you know the beginning of your curve and the end of your curve, and so for this, you know that in your reconstruction you will have that for any h, phi si of h will be equal of phi si of 0. So it means that you have a consistent parameterization on some location. So at least at the boundary of the curve you have it. But I'm assuming, I hope that we can remove it, but I think what we have is that if there is few, and in few situations you have a local consistency, okay, the number of landmark you need is given by this, then you have a global consistency. Okay, so I think this is a theorem, but okay, I write it as a conjecture. And so, what I want to say is that for instance, for open curve in 2D, this local consistency came for free just for the, at least for the beginning and the end. And if the dimension is 1 or 2, I think in fact you don't need to have this. You don't need to have this. Okay, you have automatically this thing. Okay. So I think that's interesting about this idea that with the dimensionally constrained, maybe it's make a link between this landmark and global thing, is that in fact if you at least, and I hope that we can remove some of the hypotheses here, at least if you have few landmark for which you have a consistent, in fact you can retrieve with this dimensionally constrained, you can retrieve the full parameterization. So it can be cool if we have this. 3 minutes. Oh, okay, bad. Okay, so rabbit sequence. You're happy with the... So, okay, so the rabbit sequence. I want to show you now, maybe this, I think, we know, you know that I love rabbits. So this is just a synthetic database, okay? So, and that's the way I generate the rabbits. So don't try to read that. What you see is that you have 5 random numbers, and you have this generative stuff. It's generating. Okay, it's not a linear model here. It's a non-linear model here. Okay, but you can generate a database. Now I'm running this algorithm. So the algorithm is in this sequence here is just this very simple small deformation. So there is the shooting is just you follow the straight line from you have your initial momenta. In fact, it's like the Gaussian setting where the sigma is equal to 0, and so you follow straight lines. And so what we have here is that this is the algorithm. I put dimension r equal 4. I have more pictures, but I have not so much time. And so what you see is that in red, this is the database. So in red, this is the different rabbits, and in blue, this is just the starting point in the running algorithm. So at the beginning, I think at the beginning you choose some random momenta, some random direction. And okay, so you get something which is really bad. Okay, and so after doing this this gradient descent, in fact, you see that you are able to learn from the different sample, and you can try to do the best, to try the best for dimensional subspace, just using the distortion, and you get this thing. And so you think that it's not too bad, dimension 4. But what you see is that, okay, there is some errors. It's not perfect. Okay, so this is the subspace. So we can do this for 5. Can do for 5. It's better. It's almost perfect for 5. You see, very very few. Okay, this rabbits has, but still, you know, I'm learning some kind of linear model, but which is parameterization invariant. Okay. Okay. So now we'll look at the distortion dimension, and we see that in fact it's for 5, it's not perfect, but for 6, it's good. And so now what I want to show you, okay, is for this, and maybe which is related with parameterization. So the fact here, I'm not using in any sense the parameterization. Okay, Laurent will say that there is discretization, maybe it helps, but I don't think so. And the thing is that if you look at, for instance, okay, what I'm doing here, what you will see, okay, it's not working. Yeah, what I'm doing, it's very relaxing. So you see the different rabbits, the different red, and what I have built my model, and now what I see interpolation in my rabbit space by just straight lines from one observation to the other. So what you see is that it looks very natural, the different evolution. Another thing what you see is that, look at the parameterization, in fact. I have no rigorization. I'm not saying in any way that the parameter should be regular, but you see that it's very, in fact, it's very close to some natural parameterization you have, okay? Okay, so how much time I have? 0.
Well,
okay.
whatever extra time you want to take now.
No. Okay, so maybe just it's important to say, okay, just to see about this parameterization. Okay, we can do it with noisy version, and we get, for instance, I can show you the kind of thing with dimension sex. You know, it's quite insensitive to noise. It's reconstructing. Also, we have something which looks like some kind of good parameterization in the thing. Okay, so here you see that even if you have noise, you know, it shows that we have not so much overfitting. So we can do it. I will stop it. We can do it with the full LED MM4 block here, and so we have the same property. We have that. Okay, obviously we have that. If we compare what we can get from TPCA, tangent PCA, with this, in fact, we get better results in terms of distortion. I would say that, in fact, it's with TPCA, where always the fact that you will have to choose the balance between your noise model and your rigorization before doing anything. And your result will depend on that balance. Here, we try to do the best for the TPCA. For the distortion imaging, we don't need to have that balance. Okay, and for the model selection, which is the second question, this is very preliminary, but what we say is that now if you have two different metrics, or if you have two different models, you could say now what I will do is that I will fool this kind of universal, not perfect, but universal number, which is just a dimension of the subspace, and I will try to look at the difference between the distortion I can get for the same distortion for a given, for a fixed number of dimensions. And so here we see that we have two different kernels, and we play with that. We add something, and we see that we get something which is that's clear visually that it's better. It's better using this to add a multi-scale stuff, to add 0.3. But we see that we have we can see it from the distortion. Okay, we can do it also in 3D, and the conclusion is that okay, so can we try to do use it? It's not a clear, full statistical theory, and there is a lot of missing parts. But I think it's an interesting way of thinking about trying to, if we want to work with in real situation, to say, can we try to do this model selection by computing this distortion minimization curve with this dimensionality constraint, and just say the goodness of the model I will be given by just the minimum of distortion given the dimension. Okay, thank you.
Okay, let's just take a couple of questions because coffee is getting cold out. So.
I think I started late, no?
Yeah, and you've finished late.
Yeah.
Consistency.
Okay. No, it's not a full 10 minutes.
Okay. Yeah.
In the matrix completion problem, you have to, in some sense, control the behavior of the singular vectors, ensure that they're not too sparse, and you have to somehow control it before saying you've done a good job.
You have to say the sparse. What do you mean?
You have to control the sparsity of the singular vectors of the origin, in some sense, so that you say you have
the sparsity
completed well.
No, you say that the sparsity you control. You say that the sparsity you just put the rank.
No, of the singular vector, saying they're sort of.
Oh, the singular vector. Yes. You have this. Yeah, you have this. Yes, I know.
And
you have to have the rip property.
Yeah, something similar.
Yeah.
So in your case,
yeah.
What is the corresponding sort of?
I don't know. Yeah, I know that story about this. Not clear. No, that's an interesting question. I cannot get a interesting answer like that. Yeah, I understand what you mean. That's interesting. question. I don't know. Yeah.
Okay. So, all right. Thank you again.
Okay.